Yesterday, I brought out two important representation of a matrix. Okay, a matrix can be decomposed. Decomposed is usually, used for common people. It's used in some other way, but here it means decompose means take it into parts. When you sum them together, put them together, sum them together, it becomes the original. Okay, in this case, the variance covariance matrix can be decomposed into parts, right? And there are two. I want to go back here. There are two ways of writing the decomposition formula. One is the sum of the scaled matrices, sum of the scaled matrices, where each of the matrix is we will call it as the outer product. If you want, you can write it. Okay, it is called the outer product. See, remember, I always say, you have to know English words for everything. Okay, this is called outer product. This particular multiplication. Are you able to see what I'm talking? Take the eigenvector. Yes, take the eigenvector, and then vector is always column wise. Okay? Vector is always column. Take the first eigenvector, transpose that, and then multiply this part. Right? This is called. Are you able to see my hand? This kind of multiplication. See, the column vector, transpose of that is called the outer product. Are you with me?
Yes, sir.
Okay. If you take it this way, and if you do it this way, it's called inner product. Please note it down, and you can write it in this way. Okay, so I'm going to write it here actually. Outer product. Product multiplication of vectors. Outer product multiplication of vectors, and inner product multiplication of vectors. Okay. You probably worry, every day I am learning new terminologies. Where does it going to end, right? But remember, these are the foundations of the whole science of linear algebra, which is about the multi-dimensional computations. Okay. So
okay.
Am I getting it across with you? One second, I'll write it. I'll put a picture here, how I showed my hands. This is the vector, right? You'll call it as.
Yes.
Okay. 1 second. I'll take this out. Okay. I'm going to use my pen. I think I use my pen. I can use my pen here also. Okay. Okay, let me do one thing. If you give me a moment, good notes. I have that app bought. Pretty soon I will know how to write it. See, I have bought the app in iPad. I'm trying to do that anyway. So. Okay, that's fine. Well, let's use this one. This is just a value 1. Okay, that's what this means. Value 1, value 2, and so on. Right? And then comes dot, dot, dot. Let's say value P. Right? So this is a vector. The usual representation of vector is like that. But if you do this times Oh, gosh, it won't come, Frank. It won't come easily. Okay. Let's do this anyway. And then I will arrange it. It's never easy. Okay. So this is B2. Okay. So this is how many rows and how many columns? This is P by 1. All right. So this is P by 1. And this one is, can somebody say that?
So 1 by P.
Excellent. 1 by P. So what is the product output will be? Equal to?
So it will it turn again into 1 by P? No, yes, no.
No. You are very close. Yes.
Yesterday we did 1 by 2 and 2 by 2.
Yes.
That turns.
No, 2 by 1 maybe, or 2 by 2. Okay, that's fine. Then the inner, no, 1 by, I mean, what did I do? 1 by 2, 2 by 2, or 1 by 2?
1 by 2, 2 by 2.
2 by 2. Then it becomes 1 by 2, right? So this
Yes.
one, I'm saying, consistency of such products are that inner terms should match, right?
Mm-hmm.
So it is consistent product. Otherwise, it will be a problem. But the main point is P by P. The outer will be the only one that will survive, okay? So that is the order. That is the order to remember, okay? This is the P by P matrix, right?
Okay.
So the other way to think about it, if you are confused, is a P by P matrix, right? It is a P by P matrix. Maybe I'll just write it, not to confuse with more words, a P by P matrix. Great. That is this by this. That's it. This by this, this by this, and so on, right? So always row, column. Row, column is the multiplication approach. Okay. The row is only 1 here, and column is 1, 2, 3, 4. So it will become a P by P matrix, and which is equal to, I would say, let me move it here. This is called the outer product, okay? So we can Control Z. So how it will be is, it's a matrix again. Right? I just want to express it fully. Okay. For lack of other notation, I'm going to put it here like this. Can I put it as V1? Oh, whatever. It's went somewhere. What is this? Control Z. What is this guy? One moment. I don't know what is this one is. I really don't know what is this is hanging here. Okay, so let me save and open it. It should not be, I'm not even able to touch it. This one, do you see what I'm talking about? Let me see. Oh, it's something here coming from there. Okay. So other things, okay. I still don't know what is this one is. Okay. Why it is hanging here. Okay. Sorry about that. But anyway, let me go back to my file. Here it is. So don't get distracted with that. So it is a P by P matrix, okay? So for lack of other notation, I'll put it like this, okay? V11, which means product of 1, and 1, okay? V11. Everybody understands what I'm doing here?
Mm-hmm.
And then next one will be V12. What does that mean? It's the first row here, second column here. That's what it means. Okay. The product will become like that. And let's do this. This is the problem. I don't know what is going on here. I need to. Maybe. Okay. Yeah. Thank you. So this is V1 by 1P. V1, this times this product. Okay. V1 times VP is V1P. I write it like that. So the second one will be, so it is becoming a matrix. That's all I want to convince you. Okay. You are just reviewing kind of, basics of matrices. That's okay. That's important. You have to feel comfortable, what's going on and so on. So like that, and then comes finally this VP1, that is the last row here, and then multiply each one of that with, okay. This is called VP1, right? This is called the outer product of two vectors. Okay, VP2, V2, and VP. Understood both of you?
Yes.
Both of you understand that? Okay.
Yeah.
Super. This is called outer
Yes.
product. Okay. So I'm going to call it as outer product multiplication of vectors, and I'm going to cut it out and write it in a separate another one. I will use this word later on. Okay. So please remember, that's why I'm writing all these things. See, if you know the terminologies, the communication becomes very easy, right? Inner product of vectors. Okay. Here, what we are saying, you could imagine, you could imagine that this becomes, this type of becomes in the front. Okay. It is in the front. One whole row, one column. That's it. That's the way of thinking. The inner products. All right. So say, if you are given a vector, if you want to define inner product, this is what you have to think. I will come to a very important geometric meaning here. And before that, let me complete this. Okay, the product definition here. Both are products. Okay, there is something going on. The multiplication is going on. That's why it's called products. Okay, and this is equal to, very interestingly, you can see I'm going to write it like this because I think it may say the equation. There must be math is here, but math is somewhere it's kind of hidden. Okay. So I can use the equation, it's good enough for me. So I'm going to use this kind of equation. Do you understand what's going on?
Yes, it becomes square.
Yes, sir.
Yeah, square of each of the items, okay? Right? VP square. This is called inner product. This square plus because this times this, they're all same element, right? Like that. So this is called inner product. In fact, this should become, I want it to be a subscript, better done as subscript so that it doesn't confuse. Okay. Now, F4 usually works. Okay, so like that, right? So it's easy now. You can see that the indices don't confuse you. Okay, it's kind of removed from its primary position, and usually, I am recording. Okay, it is happening. Okay, So, in fact, ideally speaking, I want to do the same thing here also, not to distract you. These are all indices, sub-indices, right? So they should not get primary position. These are just indices. To differentiate that, I would rather write it like this. Okay, so same thing goes here. There is something that works with F4 tucking. I can do it fast, but maybe it is here. Subscript. No, I wish it's there. So the very interesting thing here is, if you look at it, this one is related to distance. Do you recall that by any chance? That summation, some of the squares relate to distance. Do you recall that?
Yes, sir.
Okay, I'll come to that after it's done. Okay, so this is the distance from 0 to the vector. Okay, I'm going to do a little bit of geometry again. Okay, so have a little bit of patience, please. Okay, so let us say it's a distance from 0 to that end point, whatever that point is. Okay, distance square, rather, it's called distance square. So in 2-dimensional, well, I can also do the 3-dimension. Mentally visualizing multiple dimension is very, very important. Let us say the point is, the vector is here, right? The 3-dimensional point v1, v2, v3. Okay. Let's say this is v1, v2.
Yes, sir.
So I'm going to do. Oh, yeah, it's okay. I'm going to do this one as a 3-dimensional vector. You can call it as a 3-dimensional vector also. Just imagine it's a multi-dimension. Okay, Nini?
Yes.
Everybody think in those lines. So if this is that that 3-dimensional vector, that means pointing to some direction, right? That's another. The geometry of vectors is that, and this point, right? That is the end point. This point is what that vector is referring to. Okay, so I'm going to make it no fill. Then you know what exactly that sharp point is what this vector is about in 3-dimension, right? So the distance from here, the origin, right? This is called the origin, right? The distance from 0, 0, 0 to this point, which is represented by this, is the square root of this. So that's a geometry of inner product. Okay, refers to the, and this is the distance square. So I want to write it here. Okay. Distance of the point, distance square of the point or vector from the origin. Okay, please think of that. Inner product, that's what inner product means. Okay, the outer product, on the other hand, is this, right? This is what outer product means. That means you're keeping the vector first and then multiplying it. The inner product is transpose of the vector by the vector. Okay, transpose of the vector by the vector. So these two are, we will talk about, but more importantly, this one will be referred many times. Okay, but here what we are saying is basically, I'm coming back, two representations of matrices. Okay, one is symmetric matrix. This is a symmetric matrix. Remember that the variance covariance matrix is symmetric, right? It is weighted outer products of the corresponding outer products of the eigenvectors. So first eigenvalue, its eigenvector outer products plus second eigenvalue, its eigenvectors outer product plus third eigenvalue, like that. Okay, and then finally last eigenvalue, the lowest eigenvalue in our case, because it's a positive definite matrix. Okay, and it is weighted by its own eigenvalues. The weights tell you the importance of that particular direction, okay, in the new transformed space of observations. Okay, we say space because it could be 2 dimensions, it could be 200 dimensions. So just as common word is space. So this is one way of writing decomposing it here. The other way is, in a matrix form. This is what this other way is. Okay, so this is the second version. Okay, do you understand? Yesterday we touched on this, isn't it? The second way of writing the decomposition. Okay, the first way is just expressing each of the outer product. Second way is writing it in terms of matrices. So eigen matrix, okay, which refers to all the eigenvectors, okay, and then diagonal matrix of the eigenvalues, and then transpose of the eigenmatrix, which is all the eigenvectors transposed. Okay, so I think I showed you yesterday about that, but I think it's disappeared. No, not disappeared. I switched off the computer. So let's call that quickly to review again. A is this, I think. Yes. Okay. So I said eigen of this matrix A times, right, times diagonal of, I had to create a matrix called diagonal matrix. It's called diag. Function is diag. Okay. So eigen of A dollar, because I'm picking up only the eigenvalues, right? So these are eigenvalues. Agreed?
Yes.
Oh,
Yes, sir.
I can't do this multiplication. What is the right multiplication to do here? That is not star, something else. What is that? Say it. Matrix multiplication has a different notation. Nini, you recall?
Oh.
Yes, sir.
Okay.
Dollar into again.
Percent star percent.
Decimal. Yeah.
Otherwise it's not a matrix operation. Okay.
Okay.
So percent star percent. Again, I have to do also, it's not eigen. I had to put eigen dollar vectors, right?
Yes.
Okay, eigen dollar vectors, which is a matrix, right? And then I take the same thing, transpose there in the right side, right? Can somebody tell me what am I trying to do here? I'm trying to show that the matrix version is written like this in the command, R command, but in the let me go. There is R command. If I want, in notation, okay, it is, let's call it as E. I'm going to put some kind of matrix notation, mathematics notation here. Okay, insert. Let's see, there must be a symbol. Okay, that is what symbol. I'm going to put delta, capital delta. Okay, so which is a matrix. What happened? I have to close it. Okay, yes, I have to close it. E prime. Sometimes I say prime or transpose, right? You remember that?
Yes.
This is the eigen matrix, delta E prime.
E prime.
This is the matrix notation, okay?
Yes.
And what is E? All eigenvectors. So I call it as eigenmatrix. E is eigenmatrix. Okay, everybody understands?
Yes, sir.
Delta is the diagonal arrangement of all the eigenvalues. Is the diagonal arrangement
of all the values.
all eigenvalues, right?
Yes, sir.
Yes.
Okay. And that's it. And then E prime is the transpose. So this is the simplest way, easy way of writing it. And this is the explanatory way of writing it. And this is the detailed way of writing it.
Okay.
So many ways you can write it. The interesting thing I said here last class is that, while variance covariance is, what it means is that it is written like this means I can subtract some of these items out, and if I want to delete, eliminate, subtract some of the items, which of the items are the least contributing to this expression? The lowest scalar, isn't it?
Yes.
Lowest scalar, and which is at the end of it here. So if you want to say, I want the top two dimensions that explains this variance covariance matrix, I will only use these two part of it. If I want only top three, then I will use only these things. That's what this means. This is the meaning of the importance of the eigen directions. Okay, eigen directions. Okay. So what is an eigenvector and which is same as eigendirection? It points out to that newly transformed rotated space or translated space. It could be center is moved to some place, or it is rotated in a different angle, and say you have to keep this primary axis where most of the observations are falling, okay, or combination of both, and that is accomplished by this decomposition. You just have to center the data, rotate it to get and the rotation is achieved by these eigenvectors. Everybody is good on this one?
Yes, sir. Yes, sir.
And yesterday I also mentioned that this is for variance covariance matrix, and you can call it, this is also for correlation matrix. Okay. But in real life, you also have data matrix, and the great example of data matrix is your recommendation engine, because recommendation engine is M by N means M people are in the database and N products are in the database. In Netflix, M customers, N movies. N is, I think it is approximately 150,000 nowadays. They keep on taking a lot of money. Unbelievable. Netflix became a movie producer now, right? They're taking tons of movies. Never believed that a company can transform so quickly into a movie producing company, right?
Same with Amazon.
Amazon is also producing movies, exactly. Yeah. But it's all because of digital transformation, right? Remember, digital transformation creates unexpected angles of business possibilities for companies. Okay.
Yep.
So here it is 150,000. It used to be 100,000, 110,000 or something like that. But remember, taking a movie is not easy. It takes every year in USA we take only around 1,000 movies, less than 1,000 movies, and India is actually leading a little bit more than 1,000 movies because of multiple, so many languages, and Indians love movie watching, going to movies. Okay? They love movies. So, but even with that, it's only 2,000. And even with the Netflix coming to Netflix cannot take 1,000 movies. It's very hard, right? It's very hard. You just don't have talent, that much talent, But nowadays, anything becomes a movie, right? Somebody with an iPhone can take movies in the jungles, and then it becomes a movie, So, and it is powerful technology, The iPhone is powerful technology. So anyway, so in the case of data, this is a data matrix, but this is a variance covariance matrix, or it is a correlation matrix. Remember that. So the beauty of mathematicians is amazing. They found another method to decompose this also. Okay, so they said it is again eigenvectors, another type of eigenvectors, outer product, right? This is again outer product. Remember that. Huh? Anything we say here is a vector. That means U1 is a vector, V1 is a vector. But they are different. Okay, and it has something attached to scaling value, that is delta 1 this time. This is delta 1, not lambda 1. But they are different vectors. Okay, so it is symmetric here, but it is not symmetric here. So there are some deeper issues going on here. Again, second scalar value, and we call these things as singular values, not eigenvalues. But it has the same mathematics here in the sense that I am able to decompose, that is, take it into parts so that I can add them and get back. That is called what is the decomposition in this case. So first scaling value, highest scaling value, like before, it's also positive. Okay, like before, it's a scaling value, delta 1, delta 2, delta 3, like that. Okay, and then the eigenvectors are different. Okay, this is what is called the left eigenvector. This is called the right eigenvector. Okay, so I'm going to decompose and show it to you momentarily. Just hang in there, stay put.
Yes, sir.
And this is the second scaling singular value, like second scaling eigenvalue here. It is second scaling singular because it's one number. That's why I call it as scaling. Okay, so and its corresponding outer product is a matrix. This is also a matrix. Remember, right? Any outer product will create a matrix. Any inner product will create a cross product sum. It is variance here. I mean, this one is. I'm sorry. This one is this one is the distance square here. But this is inner product of these two. The inner product of the same vector. Okay, but inner product can be created. Your variance covariance matrix is a matrix of inner products. That's what I wanted to get to. So let me go back to that variance covariance expression. Okay. In the variance covariance expression, I just want to get that attention from you. So here, this is actually, covariance is the inner product between two different vectors. If it is the same vector, it is the distance square, or you can also call it as, it is very close to the variance, right? Because this one is product of itself, right? Covariance of x1 is same vectors. We are taking the inner product. Why do you say inner product? It's a cross product sum. That's if you put the same thing, it is squares of the same value, isn't it? So squares of the same values gives you distance square, right? Also related to the variance. Please listen very carefully. Also related to the variance, right? So when you take different vectors, then it becomes covariance. That's all I'm saying. So a variance covariance matrix is the inner product of different vectors. That's all, arranged in a nice way. Now remember that, and let me go back to this explanation here. Okay, this one, yeah, this one here. So it is the scaling again. The matrices here. I'm creating matrices here, right? With two different vectors, right? Two different vectors. That's why it and two different vectors, outer products. That's why it's a matrix, right? Again, this is a scale value. This the scalar is really the that raise that gives a certain weight to the matrix. These scales are giving weight, so it's a kind of importance in that sense, right? The weights are importance. Weights can also be said as importance values. Okay, so everything you do, you see that everything comes out to be same thing. Yeah, the only thing is that now I have to define what is meant by singular value, and I also want to define what is meant by left eigenvector and right eigenvector. Okay, which is different from here because it is the same eigenvector. It doesn't differ. Okay, and it will go up to because you remember this is not a symmetric. It is m by n, and m could be less than n, or m could be more than n. Correct? right? So
Yes.
I mean, think about this, strange situation, but we have come to the end of it. So in terms of the representation, so what we are saying is how many times you will have this? It's a minimum of m and n. So, so delta, if you want to, I have to write this here. Okay. I'm going to put it here and then change those values. What is those values are? This is minimum of, okay, I know. Don't worry about it. That's a minimum. I will change the font. Okay, minimum of m comma n. Okay, so if I change it to English, it's symbol right now. So I'll do font Calibri or something like that. Okay, that's what it means. So it will factor up to the minimum of that. Everybody, both of you, understand what I'm saying? Gaushali, are you good? Too complicated, huh?
Yes, sir, I'm here.
Okay, yeah, okay.
Yes,
So
sir.
are you with me, Nini? You're good. So the question is, where does it stop, right? I said it stops here P, but here it is. Whatever the minute. Suppose you have 10,000, let's say 100,000 movies. This is 10 million. So there will be how many decompositions here totally? There will be not 10 million, but the 100,000. This the last one will be 100,000th outer product matrix scaled by 100,000th singular value. Get it? Everybody? So far so good?
Yes, I think so.
Okay. Okay. So here is an example. I computed the outer product matrices, and it is there in the small example here. So let me put it here. Okay. See, this one, I take a vector 1, 1 and 3. I do an outer product. It has become like this. 1 times 1 is 1. 1 times 3 is 3. 3 times 1 is 3. 3 times 3 is 3. 9. Get it? That's what the outer product of that vector. Suppose I take the inner product of this, what will happen? This will happen. The answer will be, let me go here. Yeah, let me do it, and then you can tell me the answer. No, sorry. So it becomes like this. So let me take this. I should do it here, isn't it? That is what inner product, isn't it? And what will be this one? This will not be like this. What is the value? 1 plus 9, 10, isn't it?
Yes, sir.
Yeah, that is the inner product value. Okay? And the geometry of this is, it is telling you how far, the square root of this tells you how far it is from 0, 0. That vector, 1, 3 is how far from 0, 0. It's the distance. Okay. Square root of 10 tells you the distance.
Okay.
So let me write square root of 10.
Square root or square star?
Distance is square root.
Square root.
Yeah.
Oh, distance is square root.
Yeah. So distance. It says square root of 10 is the, I'll write it here. Square root of 10 is the distance of the vector, distance of this vector, okay? The vector from 0, 0. Okay?
Okay.
All right. Now,
yes.
So you remember, why do we say square root? In the Pythagoras theorem, right? the distance between A and B is A square, B square, square root, isn't it? That is the diagonal. Remember, Nini? In Pythagoras theorem, don't know.
Yes.
Okay, that's another way of saying it. Okay, so I'm going to rewrite the same way. So there is one method to write. I have more to teach you here. I will come to that. Okay, more to teach you here. What is this T? Oh, it's a transpose. It went there. It's a transpose. Okay, this transpose went there. That's why the T is looking here, right? So I don't know. It is so big. This meaning is so big here. Transpose should be closer. So I'm going to put it after. Let's see. Okay. I don't know. Either way, it is somewhat a little bit confusing, but hopefully not. I don't know. Okay. All right. You understood this singular value decomposition. So let me explain that singular value decomposition a little bit more. Okay. Now, why don't we do one thing? We'll come back to the singular value decomposition. Let me finish the PCA. Okay. Then principal component analysis. We remember we talked about the places rated almanac. Okay. Remember we talked about it. So let's go and finish that part. Okay. So when I do this one, I should get back the original matrix. This is, you see, even when I do this kind of multiplication, very complex, I got back the original matrix. It's because this is the matrix representation of the eigenvalue decomposition. That's all. That's why I wanted to show it to you. Are you good, Nini?
Yes.
And both of you. Okay, super.
Yes. Sir.
Now we were talking about this one, right? So let me see whether data is there. I wrote it as P. Okay, still it is there because I saved it. Okay, P is the places rated almanac. 329 places are rated on 9. So names of P is, these are the names. Okay, CT, housing, health, crime, transportation, education, arts, recreation, econ. And I didn't have the 9. I could have done that. Column names. I could have done that as index, but no worries because it's just the index. Okay, this is really it refers to the place index. Okay, every place is given 1, 2, 3, 4 like that. That's what it is.
Yes.
We won't use that. Okay, so I said, think about this code. Think about this code. I'm saying it's a beauty of R is that it's a function of a function of a function. You can do in one function, you can finish the whole programming if you want, if you do it, think carefully. Anyway, I take the places here. Now it is P for me. I take the columns 1 to 9. That's what this means, right? In R. Okay, I take the data frame or in this case, data frame or even matrix, you can do that. Okay. And I take the data, I take it into log transmission. Why do I do log transmission? Because variance is very big, okay? Across the across various elements, there are variances which are very big. So we want to take the log and then take the covariance of that. So that is going to give me 9 by 9 matrix. Do you agree with me, everybody? Because there are 9 attributes. I take a variance covariance among them. So it is going to be 9 by 9. Covariance means it includes variances also, okay, in the diagonal. And for that matrix, I'm doing the eigenvalue decomposition, and then I'm taking the eigenvectors and I put it in U. So U is my eigenvector matrix. Agreed? For the places data. Okay? And that's why I'm going to change it so that copy and paste is easy for me. So I'm going to write here, U is the eigen matrix of the covariance matrix of places data. Okay. And D is the eigenvalues, diagonal matrix. Okay. D is automatically, no, D is right now is not diagonal. I make it as diagonal subsequently. Okay. D is just a vector of eigenvalues. Everybody's good? Understood? So same logarithm of the values of the p-values, right? Places values, attribute values, nine attributes. So I take the log values and then do a covariance matrix. So it's a 9 by 9 matrix, and then I'm doing the eigen function for that, and then pick up the value there and put it in D. Everybody's good? So let me write it if you want. D is the eigen values only. It's not matrix. Okay? Just the values of the covariance matrix of places data. And here I'm basically diagonalizing it. Okay, I'm creating a diagonal matrix out of that. Got it? Creating a diagonal matrix out of eigenvalues. Okay.
Mm-hmm. Yes, sir.
Mm-hmm. Now, then I'm doing this. U multiplication, matrix multiplication, the diagonal of D matrix multiplication minus. That is to show that this decomposition actually is an alternative way of representing the variance covariance matrix, providing the eigenvalue decomposition does its job as promised. So this is perfectly equal. That's what I showed you last time also, right? So this will become 0. That's my point, right? So in order to show it that it is 0, because it is not, it is reading it as e power and so on, 17, 16, 15 and so on, I'll put it as round, comma, 4 decimal or even 5 decimal, it doesn't matter, 7 decimal, it will all be still 0. Agreed? Nini, correct?
Yes.
So, and that's one proof that this is the matrix, the eigenvalue representation of the covariance matrix. Okay, and then I want to do principal component. Okay, just it's called, the function is called PRComp, to find the objects in the basket of the outputs, and then I want to show you what is called the biplot. That's what I want to show. Last time I stopped there. So let me run this again. Are you ready? Let's do that.
Yes.
Okay, ggplot is not under 4 version, so I'll have to add install memory. Install ggplot. Okay. Oh boy, I think there are a lot of things that are happening, so it's going to take time. Okay, install packages, finally. All right, so I'm going to make it bigger. It may not look like bigger for you right now, so I'm sorry about that. Let me do, so it's doing a lot of packages, so it is going to ask me every time, oh, should I restart? I should have started with the installation before, but for some reason, I updated my to 4.1.1, something like that. So for that, it was not installed, and it needs to be installed for that. Okay, so it's happening. That's what is happening. So you know what I'm going to do. Here I tried to do install packages. It may still probably. Let me give probably install packages. ggplot2. It may still do the same thing. Okay. Joy. Okay, what am I going to say? One or more of that. See, more packages, that's what it happened. Otherwise, the way to do is download the package and then install, okay? So I don't know how many times, because usually it has a lot of things installed. I can also do, you know what, I can do one more thing. Let me stop this. Okay, different things. What is called, recently, Hadley Wickham has created this package. That package is called Tidyverse. Okay, Tidyverse library. Yes. Yeah, it has ggplot in that library. Let's see what happens. Tidyverse. Okay.
Yes.
If I say that, it should take into ggplot2. There you go. But it is still 3.3.5. I was built under. Okay. So package ggplot was built under version. This is what we needed. So even though this is 3.3.5. It is built under 4.1.1, so it should work now. So let me do this again, the commands. Okay, no problem. It's done. Now, what we want is, this is done right now. I explained, the rotation refers to, please note down, I want to make it a little bit bigger so that it's easier on you, right? You're not able to see most likely. It is 18, but anyway, I'll make it 24. Apply, but this one, it is too big? Okay. So 18 is okay, good for you then? 54 is what's good?
Yes, sir, that is fine.
Okay, how about you, Nini?
It's good, sir.
Okay, so thank you. So, so we have done, so rotation, the reason I'm saying is, I want you to, in the PR comp, I will write it here, okay, in PR comp. So yeah, we did LS, okay, remember that? LS is part of the programming, so you got the LS there. So I want to write here, let me do one thing. No, you are recording, I'm fine. Move on. Cancel. I want to write here. PR comp objective rotation means, okay, let me write it here. Rotation, oh yeah. So I hope you will be able to understand this PR comp dollar. What does that mean? That is, that object rotation refers to Eigen matrix. Get it? These are all terminologies. You all know so much. Right now, you should be able to understand what I'm saying, right? This is dollar. That means PR comp is the function. So that's what the objects are. The objects of PR comp, one of the objects is called rotation, and it refers to eigenvalue. Do you understand now what I'm talking?
Sir.
So I'm writing some extra notes so that you kind of understand what they mean when we use it. X refers to the data. Okay, got it? And scale refers to the scale. Center means subtraction of mean. PR comp dollar, center refers to means, right? It should be lowercase. Do you understand, Nani, what I'm writing here? What I'm explaining here? Scale refers to the output. These are the outputs of PR comp, okay? Rotation, X, center, scale, okay? The standard deviation of the attributes. So far, so good, Nini? I'm not hearing you. Okay.
Yes, sir. Now.
No, I'm talking. Nini.
Oh, sorry, I was talking on the mute.
Okay, no problem. So you want to take a break? Well, let me just stop here and then ask you whether you want to take a break, 5 minutes, and we'll come back. Okay.
Yes, sir.
So I want to finish this one before I go back to either singular value decomposition, explaining more about singular value decomposition, or the factor analysis. Factor analysis is almost the same. It's the same thing, but it is in the hidden space. We call it as latent space. That means hidden space. In the hidden space, there is an underlying variable. We cannot observe them. We observe some other variable. Okay. So go back to the observed variable, underlying variable, which you are not able to understand using the data on the observed variables, but you reduce the dimensions there to find out what's the underlying linear relationships among underlying variables are. So we'll come back. Okay. Take 5 minutes. Thank you.
Thank you. Okay.
Thank you. Yep.
Dr. Sam?
Yes, I'm here.
Yeah. Can you, if you don't mind, can you go back to that covariance, variance? Yeah, right there, that equation. I know we're trying to prove that the matrix, we're getting back to the original value, but mathematically, can you kind of explain it to me? What's happening there? What? Yeah, the second. Yeah, right.
This one?
No,
Not this.
the second from bottom.
Second.
No,
This
no,
one.
yeah, right
Oh,
there.
yeah.
Yes,
So
yes.
what I'm saying is, basically, I made a claim here that. One second. Let me see. I want to go back to that key slide, right? Where I kept on explaining so many. I kept myself sitting there explaining a lot of little things, right? It's coming. Okay, here it is, right? Yeah. So this part you understand, right?
Yeah.
Do you?
Mm-hmm. Yes.
Okay, this part you understand. What does this mean? This means, let me connect. I think it is recording. What does this mean? Basically, it is saying a symmetric positive definite matrix can be written as a decomposed sum of these values, right? Mm-hmm. And so it is exactly equal. That's the point. This is one output representation of the variance covariance in the data. This is an alternative, equivalent representation of the variance covariance in the new rotated space.
Mm-hmm.
Okay.
Yes.
And the beauty of this representation is that it identifies in an hierarchical way what is the most important direction of the data, where most of the variance is occurring, and what is the next direction perpendicular to the first direction, where next most variance angle is happening. That's what this one is.
Okay.
So that's a kind of, beautiful arrangement is made by the mathematics for you. Okay. Mm-hmm. So now, so what I am saying is that now this is the whole thing is a different representation in the new coordinate space, where it is basically rotation and shifting the origin. Okay.
Yes. Yes.
And the benefit of this is now I can leave some of the unnecessary low variance explaining dimensions from here, because I drop the bottom scaled outer product defined by the eigenvectors. I can remove them. Their effect is going to be very less, so why care? That is the benefit of this approach, right? Now, yes. So what I'm saying is that I can rewrite this alternatively as a matrix, E eigenvector matrix times diagonal of the eigenvalues lambda 1, lambda 2, lambda 3, lambda p times eigenvector matrix prime transpose. That is what this representation is.
Right.
So sigma is equal to variance covariance matrix is equal to exactly same. That's what we are saying. Sigma is equal to, that's what we are saying, exactly same. That is okay. So let me change it to a symbol. That's what we are saying. It is exactly equivalent. And if it is exactly equivalent, the minus this should be equal to 0, isn't it? Agreed? Yes. That is exactly what I am doing here. Trying to get your imagination there. Where is that? Where is that? Somewhere. I lost it. Oh, in the places. I have to go to 97, I think. Places, yeah. So here, that is exactly what I am trying to show. Now, does that make sense to you?
Yes. Yes, it does.
Okay, that's what you were asking, right? So I put a round because otherwise it will become e power minus 17, 16. It's not immediately catching our imagination, right? So I put the rounded value of this minus the covariance, right? Covariance matrix of this data, original data, is exactly same. And so let's do it one more time here. You see? The difference matrix is between the eigenvalue decomposition representation minus the covariance matrix representation, covariance matrix, just a covariance matrix of the the original data. It becomes 0. That means this is exactly equal to this. That's what I'm trying to say.
Okay.
Agreed?
Yes.
Yes, sir.
Wonderful. Now let's go back. So I was explaining. See, you have to be very careful. It doesn't matter what software you do. Two things about data analysis. You have to know the data story of the data. You have to know the story of the data. That means there is something people think, work, generate, spend time, resources, labor, everything, right? To generate, that results in generation of data. So there is a story on how the data was generated. You got to know that. If you don't know how the data is generated, you'll have tough time. The second point is the software can do wonderful for you, but you have to know what those words the software developer used it, right? I did not say these words.
Yes.
This, for example, X refers to data and so on. I didn't say that, right? But he said the software developer, in this case, PRCom function developer, they did it. They have some notation. So we have to relate to that principal components, with respect to these things. That's why I want to get your attention here also. Okay, so always, the beauty of simplicity of R is that once you apply a function, you can ask for what are its objects. That is LS, list objects. Okay, right? And rotation refers to the eigenmatrix. Okay, X refers to data, center refers to the mean, scale refers to the standard deviation. So the attributes. No, scale. It's not saying. It refers to the eigenvalues. It's a better way of saying it. I will come to that. Okay. Now you know everything, isn't it?
Yes.
So that's what is happening here. So, for example, this I called it as PVD. PVD is principal component objects. Okay. Okay. PEVD. I wrote it as P eigenvalue decomposition. That's all I wrote because I don't want to recall this again. But what does the center means? This is what it means, and I can prove it to you by saying column means of log of the p values. Remember, it took log of the p values, right? Because I took log of p values. So if I do that, it's same. You see the one? So when they center, that's what they mean. You have to know all these things. Scale, instead of scale, I will come back to that thing. So scale refers to the standard, whatever the SDEV is what they call it as. SDEV refers to the eigenvalues. That's what I want to say. Okay, so this is the eigenvalues. How do I know that? Go back to PEVD. Let me redo it maybe. Okay, so let me do this. PEVD dollar standard deviation refers to this one, and I'm telling you this is same as the eigenvalues, right? I can I can just do this. Go back to this. You remember, not this one. This one, covariance. Eigen. Okay, dollar values, right? Okay, non-square matrix. No. Oh, okay, covariances. I should have taken log covariances. Okay, so this is the variance. Let's take the square root and what it is. Yes, I think square root. Okay, you see this one?
Yes. Yes.
This is really the eigenvalues. Okay, and it is called standard deviation. It's somewhat confusing. I don't like. See, this is why you have to be very careful. This is really, when they say standard deviation, that's fine, but then you have to know how it is related to what you know, right? And these are really the eigenvalues, square roots. So eigenvalues refers to the variance, and square root of that refers to the standard deviation, and that's what they are referring to here.
Okay.
Okay. So the reason why I want to get all this attention to these values, are you with me? Gaushali?
Yes,
So
sir.
it tells me
Yes,
the
sir.
last eigenvalue refers to the standard deviation of the last variable dimension, which is last dimension. Last two refers to last two dimensions and so on. This refers to the top dimension. Okay. So
Yes, sir.
this is this is what 10 times, almost I would say 20 times, very close to 20. First value is so powerful, so important, and that's where I'm going. Okay.
Yes.
So 0.09, if you divide it, you'll know. Okay. 14 times more variance is explained by the first dimension. 14 times more variance is explained by the first dimension compared to the last dimension.
Yes.
That's the most important thing I want to share with you. So what it means is you can see last two dimensions is good enough. This plus this, right? So yes. I'm going to say. So you can say, I want to take one comma 1 2. Let's say last two only, right? We are talking about last two only, right? This refers to the last two values. Sum it. You see how functional programming works? That's why it's called functional programming. Function of a function of a function, right? I take the sum of the last two values, first two values of this divided by sum of all the values, right?
Okay.
Sum of square root of all the values.
You want to see how much is contributed.
How much is contributed by the first two? Exactly. You got it. You understand? So I won't put this here 1 to 2 alone. Everything I took, okay? I want to make sure everything is correctly connected here. This is checking it. Okay, correct. Okay, do you see what I'm doing here, Gaushali? I think Nini understood it quickly. Okay, Nini understood it. So we know all these things are. This is basically the eigenvalues, right? Which is the square root of eigenvalues. Okay, remember that square root of eigenvalues. Okay, that is the standard deviation, isn't it? Let me go back. So eigenvalues are this. Square root of that is the standard deviation. Okay, so I would rather use it. The variance, how much variance is explained, not how much standard deviation is explained. So I don't want to square root. Are you getting that, Nini? Why I am making this correction? We are talking about
variance. You don't
variance,
want
percent variance explained. Percent variance explained. Okay, not the percent standard deviation. We don't talk about standard deviation. Okay, percent variance explained. So, okay, one more time. Okay, so, oh boy. Okay, I am still constructing this, making sure my codes are right. Why is that? it's not covering. Okay, so I need to get more. No, let me see what is this going on. So here I take the first two eigenvalues only, right?
Yes, sir.
And then this is covered. Okay, this is covered up to that. That's what it is. So I don't need this one. Okay, because some has to cover up to this, and it is covering up to that. So it should be inside. This should be inside. I made a mistake there. I don't know whether you observed that. Oh, don't bother me. So many things are popping up. In the values only, I'm taking the first two values. Am I making sense now? See,
Yes.
now it is okay. Let me do one more time. Okay. So I am taking the eigenvalues of this, covariance or log of the places data, first 9 columns only, and then values. So, and the first two eigenvalues, and then divided by sum of eigenvalues, the same thing, but all. This time I'm not restricting it to only first two. Okay. Everybody is good?
Yes.
So this will tell me the percentage of variances explained by the first two eigen directions. Percentage of variance of explained by the first two eigen directions, because I'm putting it in the numerator this part, and I'm putting it in a percentage. It's percentage because in the denominator I get this. Works well. It says 82% of variance is explained by just one direction.
Yes.
Isn't it powerful?
Yes.
It's very powerful. It says the first direction itself is so much variance is explained. I'm sorry, not first two directions, not two, not one, first two directions. So if I want first three directions, then I have the same thing, everything is same, just I need to do the add. 87%.
Look at that.
Yeah. So what happens, if I do every one of this, then eventually when I put the 9, what happens? This is up to 3 dimensions, right? So if I put up to 9, then it should have what value now?
1.
1, exactly. Perfect, Nini. Okay. So you see that relationship between the eigenvalues, eigenvectors, directions, rotation, the importance, 2 different ways of rewriting the variance covariance matrix. One is the eigenmatrix, eigenmatrix times diagonal of eigenvalues times eigenmatrix transpose. The other one is outer product sum, right? Outer product sum. Did I get you, Gaushali? Okay. Gaushali, are you with me? The outer product sum, do you recall that?
Yes, sir. Yes, sir.
Super.
I'm here, Mami.
Okay. So, so sometimes you want to visually see, think about it very carefully again. You want to plot the first two direction-based transformed data only. So in other words, if I use only the first 2 dimensions of the eigenvectors, use that to see what would be the projected values of the original values into those 2-dimensional, 9-dimensional data into that 2-dimensional world. Am I making sense? You project it, that is the 9-dimensional just projected into the 2-dimensional. That is what first two eigenvectors does it. Are you with me? Am I making sense?
Yes, but sir, Dr. Sam, it seems like sometimes if you, I'm thinking in terms of R square. So
R
R square, if you add, the more variable you add, sometimes the value goes down because it's no longer.
That's right. That's a different problem. In the regression problem, right? In the regression problem, because it is simply because the amount of variance in the parameters that is created in the model, the more you put the variables, the more parameters are there to estimate, right?
Yes.
And the more the parameters more you estimate, they contribute also to the uncertainty in the prediction. Their variance is bigger than the reduction in the predictive variance due to the additional variables. That time, you get a less, it's that the predictive power goes down. So that's why you have to use adjusted R square. So adjusted R square takes care of that.
Okay.
Okay, now what is the question?
Oh, and I forgot that we're not doing the regression. That's why.
No, we are not doing this. We are not regression.
I'm like, I'm thinking,
why it is increasing continuously?
Yes.
Yes.
That we're not doing the regression.
Right. We are not doing the regression. We are doing the PCA still.
Yeah.
We are just trying to decompose, rotate the data, decompose, and explain, orthogonally positioned in the new space, how this data could be explained easily.
Yes.
So that is the purpose of this. So explained easily is your key word. They're also explaining, in adjusted R square also, we are trying to explain the variance in the dependent variable. But here, the whole variance in the whole space. Again, explaining variance. But we are talking about the whole data space. Okay?
Okay.
Good. So let's plot this one. That's the reason why, what I want to plot, I want you to think about this. What I want to plot is, 1 second. So what I want to place is like 96, 97. Okay. So what I want to plot is, recall again, I'm saying we will project all the observations into the two-dimensional rotated space, where we know the first axis explains a lot of variance, next axis, perpendicular axis, explains next lot of variance, whatever that means, right? The first lot of variance and then second lot of variance. Only those two dimensions we want to, because we want to visualize. Maybe we can visualize it in 3 dimensions, of course. But then we will take 3 principal components axis instead of 2. That's what we want to do. That is called biplot.
Yes,
If it is 3 principal components, it's called triplot. You might not have heard triplot. That means 3-dimensional plot. But mostly people don't do that. They just do only two axes, first 2 principal components, and they call it. It's called biplot. Are we ready to do that? That's what we want to show.
Yes.
Okay?
Yes, sir. Yes, sir.
So we want to consider scores. Take the PCA. X is your. So this is called projection. First PCA, PCA1. Are you able to see this one? PCA1.
Yes, sir.
The data. Take the data, project it using the first PCA. Okay. The PCA1 as data frame. So it's really the. So let me get to PCA. I think PCA1 is as data frame. Create data frame with scores. So X refers to. So I showed you. Okay, here. Okay. So what is X? We want to see this one. PEBD $X. Let's see what it is. Okay. So these are, remember, and the rotated. These are the projections already created for us. That's what X means. It's not the data. I probably said it incorrectly. These are the Eigen vectors. Okay. Do you see what I'm saying? Projected eigenvectors. In the eigenvectors, once the data is projected, see, because you see this one, the length, this is the way it is going. So let's say length of PEBD, right? Dollar X1, right? 1 is good enough. Comma 1. 329. So what it means is these are the in the projected space vectors. These are X, this PEVD $X, right? X refers to in the projected, that is in the transformed space, in the Eigen space, how these points are reflected. That's why it's called a score. So there are 9 dimensions are there, right? So if you look at X, dimension of X, okay? Or no, it won't say dimension. Let's see. N row is X. N row is also, it is not showing N row. Okay. What I want to show you is that you see that, you see that X, okay. You can see that X starts here. I asked for X, isn't it? X are columns are the eigenvectors. Let me put it this way. Okay. So then if I have to do that dimension, then I have to write it as matrix. And then it will give you here it is. So this should give you an idea for you. PC1, PC2, PC3. These are all the eigenvector values. This is the first observation. On the X in the first eigen direction, it has value minus 1.005486. In the second eigen direction, the same first observation, the original observation, is moved in the eigenspace in the second eigenvector direction as 0.96 and so on. So the rows are the 9-dimensional vector. You can see that rows are 9-dimensional, right? So that's why I want to show you the dimension. Let me do this as matrix X, and then I say dimensions. As matrix X, no, it's not X. It should be something else. PEVD $X, correct?
Yes.
You see that one? That means 329 rows and 9 columns, right? So when we transformed the data, original data, into the eigenspace, it is taking each of the 329 rows of the original data into 329 new data points in the eigenspace. It is also 9-dimensional because it has to have 9 dimensions, right? Unless there are correlations in the variable. We'll come to that later. Okay, if there are correlations, it will compress the dimensions. If there are perfect correlation between each 2 variables, let's say economics and the crime rates, perfect correlation, let's say, then the whole thing will be projected into only 8-dimensional eigenspace. Because you don't need these. In the rotation, it gets compressed. It goes away. It's just standing one axis, but where no data are around that. The whole data is spread around one in the 8 dimensions. Okay, am I making sense so far for both of you?
Yes.
Okay, good.
Yes,
so
sir.
where am I going? I'm saying in the eigenspace they are moved, right? Translated into the eigenspace, but in such a way that you are able to explain each of the angles, each of the direction as explanatory power to tell you on that direction there is most variance. Explain next on this direction most. That kind of decomposed interpretation, separated out interpretation is possible because of the eigenvalue decomposition. And so these are the what I'm trying to say is now each row in the X, which is called also the score, is actually a projected value in the eigenspace. Keep that in mind. Now I'm saying I don't want all the 9 dimensions in the eigenspace. I take only the 2 dimensions. So I can project all the points just using the first 2 columns of this matrix, score matrix. Do you agree with me? X is the score matrix. Remember that. Okay, thank you very much. Okay, there is a typo here. I shouldn't do that. Refers to the projected values of original data in the new eigenspace representation. Agreed? So if I want only 2, I can take those 2 and plot it. That is what is happening here. So I'm going to do the plot here. Okay. So first I'm defining scores as data frame. I can do data frame, or I can do, matrix and so on. So this is not PCA1, remember, mine is PEVD, right? Okay.
Yes.
So I consider it, call it as scores because it's better that way. So, and then we will plot this. Okay, that's our goal now. Library ggplot2. I want that to happen here. Okay, there you go. This is all the 100 points. I mean, 329 points. I plotted it using only 2 dimensions. See, what is this dimension? PC1 is this way. Okay. PC2 is this way. And this is the 139 point, this is the 51st point, this is the 128 point. Where is 1 here? And 329 here. Are you able to see? It's coming, it will take time. So, somewhere is here.
Mm-hmm.
We have to, where is Waldo? We have to think
3.
like that.
I see 3.
3, you see 3. Okay, now find 2. just, so you understand that I'm only using 2. So if I use the third axis, then it will become 3-dimensional triplot. But still we haven't. There's another part to it. I just plotted only the observations. Okay. Now I want to see the variables now. Let me see. Let me go back. Let me take another example. I'll come back here later. Okay. Let me take another example. I'm going to do. There is something called. There is something called US arrest data. I'm going to do that now. It's a smaller data set, so you can see the patterns easily. Okay, so and then we can go back to that one. So here is the arrest data, US arrest data. Okay. Okay, so there are 4 dimensions for 50 states. Okay, 4 types of arrests are made: murder, assault, urban population size, murder, assault, and rape, and then urban population size. These are the only 3 types of 3 types of crimes we are talking about here. The data set. Okay, let me go back to this one more time. We'll come back and let's see. So we're going back to PA2. Here's this. PA2 notes and assignments HTML. Okay. Yes, here it is. Let's see it. Let me open it. Oh, there is also PA Polarization Almanac. I have executed that. Okay. So, one moment. Okay. So library tool. So that has placed the threaded almanac. I need not have done that. That's what this one is, okay? Not this one I wanted. PA2 assignments, that's what this one is. It doesn't, but it doesn't have the what I wanted to show you. Places, USA model. I need to read the data, so I have to go back to this one, okay? So I can use the I can read the data from here. Let me show you what this is. Are you able to see my notes here? So this is about for 50 states data. This is the 50 rows and 4 variables, right?
Mm-hmm.
And okay. This data contains data in the data sets. It's there. Okay, it is there in the data set, so I don't have to worry about anything. So let me go back. USA RS. There you go. Okay, so it is there. Okay, so we want to do the analysis of this one with the PCA, right? It is already there. I don't have to. So it's part of the. This is part of R. You don't have to do additional work. R data sets. So these are the column refers to. Now I can do again covariance or correlation. Remember, I can also do correlation. Remember, right? So PR comp, I can do that. Scale equal to true. That means it will standardize, which means really it is working with correlation matrix. When I standardize scale equal to dot equal to true means you scale the data. Okay, that means it's correlation. It is working with correlation. And then I am doing the same thing. You remember this one? As matrix, rotation, multiplication, diagonal, S10, SDev. Okay, is giving a SDev. Square, that's why it is squared. Are you with me? Are you looking? Everybody, both of you understand why I put the square here? And then minus correlation, it should become 0. That's exactly what I'm showing here again, right? This means you are using all the dimensions of the new transform space data. And then in summary, as matrix. So I'm taking the first two principal components once here. That's what this means. Do you agree with me? Rotation, super. Are you with me, Gaushali? Are you with me? Okay. And do all those things. If I use this, if I use only first two, you won't get the difference to be 0. See, this I'm still differencing. A difference won't be equal to 0, but it's closer to 0. But it will be 0 if you use all of them. That's what this means, right? This is 0 when you use all of them. Agreed with me, Gaushali and Nini? Okay. And then when I use all the 4, then it becomes 0. Okay. If it's 2, it's only this much. So I'm just doing a little bit of verification for you to show it to you.
Okay.
Now, scoring using essential PA dimensions. These are the 4 PA, right?
Yes.
Okay. And I want to show you the picture for you. Okay, here's the picture. Okay. So let's do one thing. I have to redo this to show it to you, right? But anyway, it is done here. This is the part which is done here. So this basically this PR comp, nothing else, nothing beyond that. And then I call this PA1. Okay, let's do that.
Sir, so what is the purpose of using only 2 to calculate whether it's
You can use, in reality, that's what you do, 2 or 3 only, right? 2 is for visualization, that the PCA is grouping down,
Right.
these observations.
What I'm saying is like you are subtracting the.
No, the subtraction is, I will explain. Subtraction is to show that it is approaching to 0 when the difference is approaching to 0. That's all.
Okay.
Right?
Okay. That's what you were trying.
Yeah.
Okay.
Yeah. So I'm still trying to get this consistency of this thinking, right? That's all. But in reality, you don't think about like that. You want verification in your mind, in your brain. It's working, right?
Yes.
So for this US arrest, then I called as PCA1. Let's just, are you okay now? I can continue with this, right? So
yes.
you are right. You are saying, let's go and finish the work, right? Okay. I say yes for you. So I'm going to finish the work. Here is the finishing work, okay? So scores is this. I'm going to plot this. Again, plot is needed. You agree, right? To explain the visually. Okay, so here it is. Here is the let's zoom it, and you can see, because it's a less number of observation, you can see, but you can talk about it, because see, I know the states, I can explain, right? There I don't know what is 328, 329, all those things. So if I know that, I can connect with them too. Okay, now you can see, if you look at this, remember this axis is PC1. That's the most explaining axis. The PC2 is the next most explaining axis. This is the PC2 vertical axis.
Yes.
Now, if you look at this, Connecticut, Minnesota, Wisconsin, these are all northeast. Do you see this one? These are northeast. They are all grouping together from the point of view of crimes, not their northeast crimes, okay? But from the point of view of crimes, this is, they are all coming together. But even Massachusetts, Rhode Island, this is amazing, isn't it? But this is New Hampshire. But not only that, it is also somewhat rural. See, this is Kansas, Nebraska, Ohio, Oklahoma. These are all rural. Okay, so if you understand this, broadly speaking, these things. Okay, here, South Dakota, West Virginia. This is not only rural; they are also poor. You see this one? Interesting, right? North Dakota, now North Dakota is becoming richer because of oil. Montana, this is again the western rural. This is, kind of, West Virginia is in the border of everything. Okay, the east, Middle East, east, south, everything is for this one is somewhere in the middle, or nowhere, something like that. I was living there, I know. Okay, and Kentucky is a neighbor to this. Okay, so they are neighbors. So this is a rural, I would say. Okay. This is rural, richer northeast. This is rural poor. Okay, somewhere in the trying to figure out its place, somewhere in the Midwest, West, and so on, right? And here, this looks like South. It's very funny, really, right? South Carolina, Georgia, Alabama, Louisiana.
Yep.
The crimes also, the types of crimes also, you will see they are all, coming out to be. Look at this one. This is New Jersey. This is Texas, Arizona, New York. These are fairly big states too, right? Michigan, California. Okay, California is exception here. New Jersey, in my opinion, is exception here. Mississippi is exception here. But then these are all Midwest, South, rural areas. Okay, somewhat rural, mixed rural areas. Now, you have to go back, understand where the weights are in the crime. So that's where I want to show you this one. That's where you can interpret it better. So if you look at it, the PC1, is weighing, let me see. So here is the murder assault, right? Okay, this is just this one. Wait one minute. I want to come back to you. Let's go to the R and do the correlation. Basically, R plus. So you can see murder and assault go together, right? Because of high correlation, murder and assault, right? So that makes sense. Okay.
Yes.
And murder and relative to assault, murder and relative to among the murders, relatively speaking, assault leads to the murder rather than the rape. I'm sorry to talk about these gory things, but just as a data set, I'm talking about it, right? In the urban population, you see relatively more, rapes compared to assault. Okay, and you also see assaults are also connected to rapes together here, and assault and rape again. This is the same correlation. So in one way to do it, that's fine. Murder and assault is going together. Urban population goes with rape and murder and rape. So those ideas you'll be able to pick up here. That's where I'm going. Okay, 1 second. So look at this one. So this is a kind of urban area: New Jersey, California, Arizona, New York, Texas, part of Texas, and so on. This angle. So you have to interpret that. So mostly it is about, we are talking about urban, right? So it's about rape. Okay, 1 second. Oh, here it is. What happened? Here, I have to go back to this one. Correlation, right? I was talking about correlation. So, okay.
Yeah, right there.
So this one is high rape and assault go together, makes sense. And then murder and assault go together. The urban population is mostly about rape, relatively speaking. Okay, some assault and relatively speaking, but less murder. That's very interesting, right? Less they are correlated to the murder. So that's what you are seeing here. What we are saying is in New Jersey and California, you will see that kind of crime here. That's what, and they all go together. The states, New Jersey, California, New York resemble together in that sense. Okay.
Yeah.
Even Delaware is in the middle actually. So I would say only this. Okay, these things. It's remember this. This means less. The PC2 is less. The PC1 is high. Okay. PC1 is negative. Sorry. PC1 is negative. PC2 is also negative. Okay. Relatively speaking, after you add, relative to the whole country, they are having negative values here, less compared to the centered value here. So if you look at it, Florida is probably the worst case here. In the second dimension, listen very carefully. The second dimension is explaining. Okay, second dimension refers to my Eigen vectors. Okay, so I have to go back to this one. Yeah, second dimension. So you can look at these Eigen vectors. We are only talking about PC1 and PC2 only. Okay, we are not looking at PC3 and PC4. So look at these values. Where the most of the crimes are happening in terms of positive versus negative values. Okay, positive means more, negative means less. Even that we are talking about, the New Jersey and so on. It is less than national. That's what it says. Okay.
Okay.
So, and I just showed you some examples, because you have to look at these values, PC1 versus PC2, negative or positive, in terms of values, but visualization is much easier for you. Behind this. Visualization is much easier for you, so you can find out this, it is PC1, is more, negative here, New Jersey, Massachusetts, Rhode Island, California, and PC2 is high here, North Dakota, Vermont, and Virginia, and they're all going together in terms of the the region basically specifies the type of crimes that we are doing. So we have to go back to the data again, let me go back and talk to you from the data point of view, okay? USA arrest, then you will know better, okay? So if you look at this one, I said California, look at this one, murder is 9, right? Assault is 276. I'm talking about raw data. No, you have to take the standardized value. That's where we are talking about those negative values and positive values. So this is let's compare this California with what is that we were talking about here? California. This is California. Let's say go to the North Dakota. Okay, California. This side, the opposite side is West Virginia. Let's take that one. California versus West Virginia. 9.0 here, 276. Okay. Rape is 40. Let's go to West Virginia. West Virginia is 5.7. Instead of 276, it's 81. Okay. But the problem is your urban population is 9.3. Right? I mean, urban population is, I don't know why this
40, I think, or
66. So let me compare these two, West Virginia and California, because they are in the opposite spectrum. Okay. So this is West Virginia, right? And then let's take the California. So you have to make sense out of this. That's the only way you can win the listener's heart, because they want you to explain this thing, right?
Yes.
The last one is rape. Okay, urban population is the third one, murder and assault. So let's do that. Copy and paste it here. Are you listening, Kaushali? Are you there? Okay. So what we are saying is that now this is murder index. This is assault index. It's a lot of assault going on here, and also it's a huge state. Okay, it's a huge state. A lot of assault is going on, and then some amount of the murder is going on. Look at, but surprisingly, it's very high here.
Yes.
Isn't it? West Virginia, relative to the population.
Population, yeah.
Yeah, so too much, right? This is 5 times very close. If you multiply this 5 times, you are double this one, right?
Yes.
If you multiply this 5 times, 25, it's 3 times this one, right? So if you make 5 times, this is unbelievable. West Virginia. Actually, the crime, and for the first time, I'm also interpreting it very harshly, right? Because West Virginia is pretty bad.
Yes, it is.
Compared to California. And that is what is, captured here in this picture for you. Okay. So that's why it is so, opposite here. This is relatively so low compared to the population and everything. So let's compare with the, how about Texas? Because then you know you are coming closer to this and also it's still away from this. Or you can compare South Carolina, or you can do Wisconsin. Okay. So let's do the Wisconsin comparison. Just one more. Is that okay?
Yes.
Wisconsin government. So your mind should be thinking about certain numbers there. So Wisconsin is this.
It's low.
Yeah. Low on one side, but high on the other side. It's low on the PC1, but high on the Wisconsin is high on the other side, right?
Yes.
Higher. So compare this one now.
Yeah.
So this is this population is 5 times, right? This is 4 times, right? If you multiply this 4 times, the population is 4 times here, right? In California. So if you multiply this 4 times, it comes to around 200 here, this is very close here, but this one is way, okay. That is interesting. What is the fourth one? We are talking about the fourth one is, rape. G. Very, okay. So that is why you have to interpret it. No? So you can see that. That's the reason why it is here. So this axis is more about rapes. The right side is more about rapes. This is the lowest, best scenario. So California is not bad after all, right? It looks like a good state.
It looks like, I would think that it happens there more.
Yeah, I was thinking too. And actually, Nevada and California are all great states in terms of the crimes. That's the kind of conclusion you come after doing this kind of analysis. And of course, only 4 parameters, 4 columns we are comparing. It could be 100 columns, and yet we can see some patterns here. Amazingly, humans are highly predictable. Let me tell you this. We think that they are not predictable, but broadly speaking, we are predictable. That makes sense, right? It's about broadly speaking.
You cannot judge a person, though, can you?
Not person. But what I'm saying is, when you will know, you can judge a person when you are going to the extreme situations. Yes or no? Right?
In extreme situation,
yes. In
yes.
extreme situation, yes or no? You get lots of little details, put them, and then eventually we'll come to the conclusion, well, you know what? He has some health issues, he has mental issues. That's what happens, really, right?
Yes.
Who in the world with the right mind will do a crime against other people? You don't even do it against an animal. You're not supposed to, right?
Yes.
You don't beat a dog. You don't beat a cat.
No.
Why would you do it for an animal, a person, right? Who is more sophisticated,
yes.
but under stress, all kinds of what should I say? Yeah, unusual thinking. People do make mistakes. Or they are angry with something and they show it somewhere else. They are frustrated with something, they show it somewhere else. That's how it happens, crimes. But you cannot judge on the basis of what their background is, because everybody will, almost everybody, I would say 95% of people, right? Almost 90%. 5% of people still, they will at best, they will retreat to themselves if they're angry. They don't want to talk about it. They don't want to. They go close quarters. They take it themselves on themselves, and they go to hospital.
Yes.
They get a heart attack and they go to hospital. So the point is, I made a very broad comment saying that humans are predictable. I think everything is predictable, and that shouldn't surprise coming from me, right? I'm a predictive scientist. Okay, so I'm biased maybe, So I think, Kaushali, are you there?
Yes, sir, I'm here.
Okay, you have been listening.
Yes, sir.
Did I confuse you?
No, sir. I'm listening to.
So, in the next class, there are 2 things I want to address. This kind of stuff we will always do for dimensionality reduction. It doesn't matter what dimensionality reduction we do. Okay, point 1, biplot. Not only biplot, you can do triplot here. That means the 3rd PC component will be there. Are you with me? And then you can rotate it and so on. Nobody does it. We can do it.
Oh, okay.
And that's what they do in t-SNE. Okay, t-distributed, separated. It's called t-SNE. I'll tell you.
Okay.
And also now there is a new method called UMAP. All these things, try to visualize versions of data into its, so that we can see the separations among them. Okay.
Okay.
So we want to understand from that perspective. The other one is, I want to go back and explain to you the SVD, singular value decomposition, because we are going closer and closer to more sophisticated analysis. Okay, image decompositions, and also voice decomposition. Nice. Yes, image decomposition, voice decompositions, and but image decomposition we can also do PCA. Okay, remember If you want to directly work with data, then singular value decomposition is useful. If you work with variance explanation, most of the important features, right? Variance, and the variance is the important features. Then you work with PCA, and we have few other visualizations about PSNI and UMAP and so on. But I won't go into detail all those things because we don't have enough time. We have to go to the foundations of it first, more and more, and so that you understand, you can think independently. For any given problem, how to resolve. Why is that it's coming? What is that I have to look at it? In terms of the objects of the output and so on. Okay.
Yes.
So with that, we'll see tomorrow. No, not tomorrow. Today evening, we will continue with the singular value decomposition and factor analysis. So in the direction of PCA, I want to move in the factor analysis, which is about the latent principal components.
Okay.
Okay. And in the direction of matrices, I go to SVD today and tomorrow morning. Tonight and tomorrow morning. Okay.
Okay.
Okay, sir.
Any questions?
No, very good, sir.
Awesome.
Okay. So I hope you liked it, and hopefully you will use these things, in your job quickly. Okay. Otherwise, you'll forget.
Yes.
Okay.
Yes, sir.
Are you going to do some work in data science, Nini, in your company?
I hope so. Because right now I'm trying to network with people that are related to.
Let me know if you want me to speak with somebody politely. I don't mean anything, because you need to have a chance also, right, to practice.
Yes.
Okay.
So I don't know. Tomorrow I'm gonna talk to my manager and see if I can apply for a position. It's called enterprise. I think it's like, I don't know if it is enterprise manager or enterprise data manager. So it's related more to database.
Okay.
Congos and Tableau database, and getting the reports. So I'm gonna try and apply.
So you need to be very good at SQL.
Yes, it's also asking for SQL. Yes.
SQL they will do, and they are also asking for data science.
No, they're asking for like a Congos, IBM Congos.
Oh, Cognos,
Yeah. And Tableau.
Not and Tableau or not Tableau.
I'm sorry.
And Tableau or not.
No.
And
Tableau
Tableau.
included?
And Tableau. Okay. So you have to know SQL and Tableau. Yeah, absolutely.
They want.
But Cognos is also its own application. I don't know whether you have training in that.
No,
Cognos.
I don't. I've never seen it before, so I have no idea. But it has more to do with the databases, and so. Yeah,
it will create summarized, cubes. It will work with summarized cubes. Yeah.
Okay.
So continue to do your work here. Get experience, and then you can confidently talk. What are the 10 things you can do? You can say that, right?
Yes.
How to reduce the dimensions of the data. How do you model the regressions? Classifications. How do we do Spark? You have to wait until Spark is done. We have Spark course also. Cluster computing.
Okay.
Anyway, keep your cheers up and continue to learn. And we'll meet today evening. Okay.
Okay.
All right.
Thank you.
Thank you, Gaushali. How is it going for you, Gaushali?
Yes, sir. Fine, sir.
Okay. So we'll see today evening. Okay. In my time evening. Take a good care. Sleep well tomorrow morning for you. Yeah.
Yes,
Bye.
Bye.
Bye, both of you.
Thank you.